All right, today for geometry, we've got 2.6. We're using proofs, doing proofs using segments. All right, so our objectives are to prove and apply theorems that are involving points, segments, and lines. We're going to state and prove that segment congruence is an equivalence relation, pardon me. All right, so in this section, I love that it has some scripture in there that says the Bible says that we are to work diligently at the task set before us. Gives us some verses there, some scripture. So Genesis 2:5, Ephesians 4:28, Colossians 3:23, and 2 Thessalonians 3:10 through 13. If you read through those, it sums up to be one must be diligent and have perseverance to succeed. That is like the best advice I can give you for algebra or for geometry, I'm sorry, is just to be diligent and have perseverance. Like I know that it's just kind of a foreign math all over because we're doing proofs and proving these steps and things. So I know that it's brand new, very different from any math you've done. I get that, but just continue to be diligent and have perseverance throughout the year and you will do well. All right, so some helpful steps, okay, to proving theorems, because sometimes we'll have to do that, but just in general, like proving, like doing your proofs, okay? So identify your premise, that's your given information. Identify the conclusion, okay, that's what you're trying to prove there. So we've got a premise and a conclusion. Then make a sketch, okay? Draw yourself a picture. Make sure you understand what they're asking or you're looking for. Step 4, consider any related definitions. Okay, those are going to be super important. Properties that you might recognize, postulates or theorems, because remember, you're always trying to use inductive and deductive reasoning. So looking at it, being like, oh, I know this about it, or work whatever. And step 5, don't feel bad if you want to work backwards from the conclusion. Okay, that is a problem-solving strategy that we talked about in Algebra 1 and hopefully you've used for years. But don't be concerned if you need to start at your conclusion and work backwards. That is totally fine. All right, I have included a couple of older definitions in here from pages 19 or 25 and then page 24 because they will be helpful. Okay, so we have the definition of between, first of all. Okay, so point P we know is between R and S, which is denoted R-P-S. Okay, so if I were to draw a picture of that, that means I have R and S here, and it says point P is between that. Okay, so just denoting it this way. If R, P, and S are collinear, and it says ray PR intersects ray PS at point P. Okay, so if they intersect at this point, or we might say PR, so the length of P to R, so this length in here from P to R, plus the length of P to S, so from P to S is equal to the whole length, so from R all the way to S. Okay, so those things make sense, but we're going to use that definition of between, okay, so we can use this formula. The other definition I included is congruent segments, okay, which just means segments with equal lengths. That's the definition of congruent segments. So again, these are definitions. So where it said things, that you might consider, and it had definitions. Okay, these are two definitions that might come in handy today. Okay, then we've talked a little bit about a two-column proof already. Okay, the two-column is the most common. The statements are easily identified when written in that if P then Q format. Okay, so what they're going to have is they're going to have the statement of the premise, the statement of the conclusion. We're going to have a diagram. It's that two-column. You might have a diagram with it, and then you're going to have your columns for your statements and your reasons. So remember, it's going to look like this. Has statements, reasons. They usually give you the given premise, and it says prove, and there might be a diagram over here included. All right. Any equivalence relation, remember, this is going to keep coming up. Any equivalence relation exhibits the reflexive, symmetric, and transitive properties. Okay. All right, let's get into example 1 then. So we have some new vocabulary and just some new things here with segments. Example 1, it says prove a line and a point not on that line are contained in exactly one plane. Okay, so here's the thing. The example is actually the prove part. This part here I included for your benefit. I broke it down into the given and the proof. Okay, but you could take what it says here, when it says example 1 proof. A line and a point not on that line are contained in exactly one plane. And you could come up with the given for that. Okay, so the given is there exists a line K and a point P not on that line. See, because that's what there's a picture here, a diagram. So we have a line K and a point P that's not on that line. We're going to put that in our first statement. So there exists a line K and a point P not on that line. Okay, and that's given information. Then we know what our proof is. We're going to prove there's exactly one plane Q. Okay, so we're naming that plane containing K and P. So that's going to go on my last line of my statement, right? Because that's what I'm proving. There is exactly, and that X didn't turn out very well. Okay, exactly one plane Q containing K and P. All right, and we can't give any reason for that currently. All right. So now on this, okay, so if we're going to build off of this, we need to use some other things that we know. Okay, so if you would look back at old notes or if you have, what can you apply? What information can you pull from here or can you think back on? So if I said, hey, what if you looked at the expansion postulate? Okay, that was from chapter 1. It's actually 1.3.1 if you want to look it up. Okay, it says the expansion postulate says a line contains at least 2 points. Okay, a plane contains at least 3 non-collinear points. We're not talking about a plane. And space, we're not talking about that. But we can use that information from the expansion postulate that says a line contains at least 2 points. Okay, and we could put some points on our line. Okay, so that's what I'm going to do. I'm going to use this expansion postulate. And we're going to say, okay, our line K, I'll put that in there, contains 2 points. All right, and so we're going to put 2 points on line K. So I'm going to put an X and a Y. Okay, and so that's what I'm going to say here. Line K contains 2 points, X and Y. Okay, because again, I'm trying to prove that there's exactly one plane, Q, containing Q or K and P. Point P on line K. All right, well then, if we look at the points that we've got, okay, we need to think about point X and Y. Those are collinear. Is P collinear too? No. All right, so they're non-collinear. So I'm going to say X, Y, and P are non-collinear. Okay, and that's just the definition of non-collinear. So I use the abbreviation def'(N) for definition of non-collinear points, PTS. Okay. Okay, so now I've got these non-collinear points. I'm trying to prove that they're a plane, so maybe I should look at some vocabulary or something with a plane, because I have a plane postulate, right? What's the plane postulate say? So if you look that up and reference it, it's 1.3.3. Okay. The plane postulate says 3 non-collinear points lie in exactly one plane. Well, look at this. I've got 3 non-collinear points, and that's exactly what I need to know to prove that there's exactly one plane that contains them. Okay, so I'm going to use the plane postulate. Okay, because again, that plane postulate says 3 non-collinear points lie in exactly one plane. So I'm going to say points X, Y, and P, all right, create exactly one plane. All right, so how am I going to get to this last one? There's exactly one plane Q containing K and P. Well, that's kind of the same thing that I said. Let's look back. A line and a point not on that line are contained in exactly one plane. There's exactly one plane containing Q and, or K and P. Oh, because we haven't included the line yet, right? We've got these 3 points on a plane. We have not included our line yet. That's what we've got to get. We've got to get our line in there. So let's look at the flat plane postulate. The flat plane postulate, 1.3.4, says if 2 points lie in a plane, then the line containing those 2 points lies in the same plane. Okay, because we've got points X, Y, and P are in the same plane, but my flat plane postulate, okay, is pointing out if 2 points lie in a plane, then the line containing those points. Well, now, since X and Y are in that plane, the line containing the points, which is line K, lies in the same plane. So now I need the flat plane postulate to help me, because now I'm talking about a line and the point. So the line, I had to get the line in there using the flat plane postulate. Okay, so takes a little time to look back at these definitions and know what they are and how to use them. I totally get that. We're going to get more and more familiar with them as the year goes on. All right, so let's clear that, and we'll go to the back and try some others. So now we have theorem 2.6.1. Its segment congruence is an equivalence relation. Okay, so again, we talk about all these things that are equivalence relations. Okay, so the following proof emphasizes the difference between sets of points, which are congruent, and their measures, which are equal real numbers. Okay, so the definition of congruence is frequently used to switch between congruent objects and equal measures. This is helpful. The definition of congruence, okay, which was on the front, is frequently used to switch between congruent objects and equal measure. So here's the thing. Again, this proof, example 2, is going to emphasize the difference between sets of points, which are congruent, and their measures, which are equal. Okay, so sets of points are congruent. Okay, their measures, we say, are equal. That's important. You're probably like, what? It's all the same, but it's not quite. All right, so let's look at example 2. It says, prove the symmetric property of congruent segments, so that we're going to prove that they're symmetric. So we're given that segment AB is congruent to segment CD. All right, so we're going to say a segment AB is congruent to segment CD. That's given. All right, we're going to prove that segment CD is congruent to segment AB. Okay, we're proving that. We know that there is this congruent symmetric property, but we're going to prove it. And the way that we do that is we say, okay, so this is saying the segment, the object here, okay, is congruent. We want to switch and say that they are equal measures. Okay, we're going to switch between the objects and the actual measures. So we want to say the measure of AB is equal to the measure of CD. Okay, that is the definition of congruent segments. See, that's what it just said up here. Okay, we're going to use the definition of congruence, or in this case, congruent segments, frequently to switch between congruent objects, so the segment, and the equal measures. Okay, then we could say we know that this is symmetric property of equality, right? If AB is equal to CD, then we know that CD is equal to AB. The measure of CD is equal to the measure of AB. That's the symmetric property of equality that we've talked about. Okay, and then if we know that the measure of CD is equal to the measure of AB, we can go back and say, oh, well then segment CD is congruent to segment AB, which again is the definition of congruent segments. Okay. Also, I will start using some abbreviations for congruent. I will use the congruent symbol in there. So I'll be like definition of congruent and put the symbol in there, segments. All right, now let's look at example 3, where we're going to do a little more work with it. So again, in this 2-column proof, we've got the given, the conclusion, a lovely diagram, 2 columns, 1 for statements, 1 for reasons. Okay, your first statement and reason are always the easiest to give, and the last one, because it should be given. All right, so in this one, we are given that segment LM is congruent to segment PQ. All right, so that's given. And we need to, so we know LM is congruent to PQ. Okay, and then we're going to prove that segment LM, pardon me, LP. I didn't think that sounded right when I said it. So LP is congruent to segment MQ. All right, so the first thing that we can do, just like on that previous one, is we can switch from the object, saying that the objects are congruent, to saying their measures are equal. So we're going to say LM is equal to PQ. So then I could say, okay, L to M is equal to PQ. I can put those markings in there. And my reasoning is it's the definition of congruent segments. Okay, then I've got to look at my thing. So I'm trying to prove, I want to prove that LP, L to P, is congruent to M to Q. Okay, so let me mark that. I want to prove that L to P is congruent to MQ. Okay, that's what I want to do. So I'm kind of changing my colors there. Well, it seems like then that I need to include something here about MP. Okay, so this piece here, because it's in both of these, I need to bring it into my proof. So MP is equal to MP, because we're going to put on there that it's equal, whether it's MP or PM. You could rewrite it if you wanted to, but however, so this is that reflexive property of equivalence, or of equality, however you want to say it. Okay. Then I'm still trying to get to LP. So how can I get from LM to LP? Oh, what if I add them? What if I say LM plus MP would equal LP? Right, so I can say LM plus MP, just like up here I had MP, is going to equal LP, because I've got LP down here. Can I do that? Could I do the same thing for the other side? Could I go ahead and say, because I've got PQ and I want to get to MQ, so I could list the same thing because it's going to be the same reason. I'm going to say PQ plus MP is going to equal MQ, although that's kind of in a weird order, isn't it? I feel like I should reorder these, switch that order around, because MP comes first. So how about I say MP plus PQ equals MQ. So we've got, does that make sense there? That we're adding those? So that's the addition property. Hold on. Hold on, is that the addition property? LM plus MP equals LP. Yeah, that's the addition property. Okay. So the addition property of equality there. Okay, then what are you thinking after that? Okay, well, maybe I gave you too much think time. That's okay. So then if we said MP, right, equals MP, and we added MP to both of those, right, MP is PQ, I may have too many steps here. We may not need 7. I know the book uses 7, which is okay. You could do, but we may not need 7. Because since we added MP to both, we can say LP is equal to MQ, because we did substitution. Okay. And then we can, because we know that the measure of LP is equal to the measure of MQ, we know the segment LP is congruent to segment MQ, which goes back to that definition of congruent segments. All right. So we kind of skipped number 6. Again, the book had it. Sometimes I don't always agree with the book that like we have to have as many reasons as they do. So I think that you could get there just like that and it would be okay. All right. So great job with that, and I will see you later.